Good afternoon, everyone. I hope everyone can hear me. Welcome at yet another Lunch and Learn organized by MNext. And today I'm especially happy because for the first time we also have a guest, a speaker from all the way from Brazil. Well, actually he is in Brazil, but sending from Brazil as one of the partners from the Living Lab Biobase Brazil. So first a bit about the program of today. Currently I'm working on the introduction and then we have the presentation of Dr. Mateus Save Silva from the University of Ouro Preto of about half an hour, and then the final 50 minutes of this Lunch and Learn we have time for some questions and discussion. I would like you to ask your questions via the chat. I will all note them down and then I will ask the questions to Mateus later on. So feel free to post all your questions and thoughts that you have based on the presentation. Of course, the presentation slides will be shared afterwards. And you probably already noticed that this Lunch and Learn will be recorded. And also good to mention that we would like you to keep your camera off and also your sound off so there is no disturbance during the presentation. So to first introduce our speaker of today, someone I met when I was during my half year in Brazil in the past semester. Which is Dr. Mateus Save Silva. Mateus, he studied chemistry at the Universidade Federal de Minas Gerais, UFMG in short. And after he finished his master, he also pursued his PhD degree at this university with an emphasis on physical chemistry and theoretical and computational chemistry. Currently, Mateus is working as a postdoctoral researcher at the Federal University of Ouro Preto, UFOP, where I also spent some of my time the past half year. And there he is part of the group of physical organic chemistry. And together with his colleagues, his research colleagues, Mateus focuses on the development of biocatalysts and bioadsorbents from cellulose derivatives. And today, obviously, Mateus is going to tell a bit more about this research with a specific focus on the role of computational chemistry in this research. So welcome, Mateus, and I would like to give the floor to you.
So hello, everyone. Good afternoon. First of all, I would like to thank Professor Yappi for the kind invitation for me to give this talk to you, and thanks to everyone that attended to the presentation. And thank Professor Yappi for the kind presentation. So I will share my screen now, so that I can put here my presentation. So is it okay? Are everybody seeing it?
Yes, we can see it clearly.
Oh, nice, thank you. So Professor Yappi has already kindly introduced me. So again, my name is Mateus. I am part of a group of physical organic chemistry under the supervision of Professor Leandro Gurgel at Federal University of Ouro Preto. And I've got my PhD in chemistry from the Federal University of Minas Gerais, which is located in the city of Belo Horizonte, the capital of the state of Minas Gerais, where I currently live. But I'm currently working in the city of Ouro Preto. Here's a picture of the city, and here's a picture of the building where our laboratory is located. So I'm actually a physical chemist, and I've been working with computational chemistry for a while. And throughout my career so far, I have already studied metallic clusters. I am also interested in the chemistry of phosphorus in the interstellar medium. And I have already approached nitrogen atomic clusters, also known as polynitrogens, which have been attracting the interest and the attention of the scientific community for being possible good candidates for high energy density materials, because they can store a large amount of potential energy within their chemical bonds. And maybe we can talk a little more about this further on my presentation. But the project I am currently developing within my research group is related to a computational approach to model the interactions between some specific metal ions and cellulose derivatives, which are materials that are being produced by the group for application as biosolvents in contaminant removal. So our goal is to investigate the adsorption mechanisms of these specific metal ions on the surface of these bio-based materials, which are produced from plant biomass. So our main motivation is the quite common contamination of water bodies due to human activities. So here on the right, we can see a list of typical human activities that generate wastewater containing several types of different pollutants. Such as mining, electroplating, petroleum refining, smelting, fertilizer and pesticide use, and also the electronic industries. So significant portion of the pollutants consists on metallic ions. So, for example, copper, chromium, zinc, mercury, lead, and up to a certain extent, to a certain concentration level, our organisms actually need this. But if humans are exposed to beyond a certain limit of these concentration levels of these materials, it can cause diseases and disorders. It can interrupt and alter physiological functions. We worry about this because of their toxicity and carcinogenicity, and differently from what organic compounds can do, there is an additional problem here that metal ions, they are non-degradable, right? So they can bioaccumulate over the food chain. But before we go a little deeper into this topic, I would like to give you an overview of some interesting applicabilities of computational chemistry. Let's start, for example, with material science, where, for example, computational chemistry can assist the design of new materials. Let's say, for example, nanoclusters, which are essentially aggregates of tens to hundreds or even thousands of atoms, which present physical and chemical properties which are strongly dependent on their composition and size. And so we can use computational chemistry to obtain their electronic structure and to calculate the energies and to investigate how these properties evolved as these particles grow or as their composition change. So we can seek for what we call magic numbers of composition or size that can produce notoriously stable structures or enhance some specific property, so that it can guide experimentalists toward the most promising structure or the most promising material according to the desired properties. Another interesting application is related to SERS, which stands for Surface Enhanced Raman Spectroscopy. It is an experimental technique to detect and identify even a single molecule. And this is possible because we can adsorb this molecule onto a metallic surface, usually silver or gold. And this metallic surface can act as an antenna due to a phenomenon called plasmonic resonance. And this antenna can amplify the signal related to the interaction of that molecule of interest and the incoming electromagnetic radiation. So we can use computational chemistry to model these adsorption of this molecule of interest on the surface of this metallic nanoparticle. Another interesting application, we have the quantum dots, which are essentially nanomaterials that will also exhibit size-dependent properties, more specifically optical or electronic properties due to a phenomenon called quantum confinement. So depending on the nanocrystal size, we will have different energy band gaps. So the electronic transitions taking place here will absorb and emit some specific wavelengths of light, so we can have different quantum dots presenting different colors like this. They have several applications, interesting applications such as lasers, solar cells, LEDs, photocatalysts, so on and so forth. So with computational chemistry, we can unravel this band structure of these nanomaterials and again help designing new materials with specific properties, specific light wavelengths that it will absorb, and so on. If we go now for a more, let's say, fundamental science perspective, we can also use computational chemistry to study the interesting chemistry of phosphorus. And why is it interesting? Well, phosphorus is essentially always present in molecules which are essential for life, at least the way we know it. And it plays a key role in the chemistry of living organisms, right? So we can have here, we have here a picture illustrating the DNA structure and this linkage made by phosphate here. These bonds are really strong, and exactly due to this high stability of these phosphate esters here, we can have long-term storage of genetic information because this will allow the formation of these very long polynucleotides. Another example of the importance of phosphorus in biochemistry is this quite well-known macrostructure, which is the phospholipid bilayers that usually make up the cell membranes, right? And which these phospholipids are actually made by let's say a hydrophobic tail and a hydrophilic head, and this head has a phosphate anion. And I can show you how computational chemistry can be used to simulate such systems. So here we have an example of a completely disorganized ensemble of phospholipids and water molecules. So the water molecules are represented by these white spheres, while the phospholipids are represented by these strands here. These pink parts represent the hydrophilic heads, and these green, bluish parts represent the hydrophobic tails. So we can run some molecular dynamic simulation. Here you can see several snapshots of this simulation, and we can see the self-organizing structure spontaneously self-organizing itself, so that the bilayer is finally formed with the hydrophobic tails pointing inwards and the hydrophilic heads pointing outwards, and we can see the water phase both up here and down here. There's also another interesting video I would like to show you. Here you can see these are water molecules, and this is the phospholipid, the bilayer with some proteins, and we will see hydroxycholesterol being pulled off from the layer to the water phase. You can see it from molecular dynamics. So all the water molecules solvating the system outwards, and the bilayer here. So this like orange yellowish molecule is the hydroxycholesterol being pulled off from the inside of the phospholipid layer to the water phase. You will see by the end of the simulation, you will be able to see this hydroxycholesterol going out. So this is actually a huge system. There are millions of molecules here. This is not easy to simulate. So I would like to show you. Let's get back to the presentation here. I would like to show you that indeed in molecular modeling, we usually can divide it into essentially two different domains, the domain of molecular mechanics and the one of electronic structure or quantum mechanics. So on this side, the underlying physics is based on classical mechanics. So we integrate the Newton's laws to simulate the dynamics of a system. While on this side, we will have to solve the Schrödinger equation to study the system. So we employ quantum mechanics. Within molecular mechanics, electrons are not explicitly treated, and atoms are usually treated as spheres connected by springs, while within the quantum mechanics domain, electrons are usually explicitly treated, and atoms are treated as positive nuclei plus an electron density. On this side, we will have a low computational cost, and we can do fast calculations so that we can approach large chemical systems, such as proteins, polymers, and membranes, as I have just showed you. But on this side, we are constrained to small to medium system size, usually small molecules, clusters, or oligomers to represent polymers. And on this side, we usually depend on pre-derived force fields, parameterized force fields, while on this side, we usually employ first principles with no empirical parameters. Actually, I need to emphasize that sometimes density functional theory, which is considered an electronic structure method, actually uses some parameterized functionals, but it is still essentially an electronic structure method. So on this graph here, we can see that the amount of physical detail that we have against cost of calculation. So if we want to have too much amount of physical detail, we will need strong, powerful computational resources. I am not very, I don't have too much expertise within molecular mechanics. I usually work within the domain of electronic structure methods, employing density functional theory and some correlated methods. So we can kind of combine these two worlds, let's say it like this, and we can employ what is called quantum mechanics, molecular mechanics. So we will have a classical molecular dynamics acting on the biggest picture, but we can find some specific sites, for example, the site of interaction of a specific molecule with a specific site of a protein, and then we can employ quantum mechanics to treat just this part of the system. Coming back to the phosphochemistry, why am I am calling it astrochemistry? Well, because a great mystery in science is how phosphorus became biologically available on Earth. How did it move from an essentially inorganic chemistry to being so important within biochemistry, right? So the way to study this is to turn ourselves maybe to the environment where we could find the most primitive chemistry going on. So we turn ourselves to the interstellar medium. We believe that phosphorus is formed by nuclear fission inside massive stars, and it is expected to be released to the interstellar medium by supernova explosions. And some phosphorus-bearing molecules have already been detected towards some molecular clouds in outer space, and also towards solar-type star-forming regions. So we use these observations, and we try to simulate the conditions of these molecular clouds, running astrochemical models, so we can investigate the chemistry of these molecular clouds to provide insights on the primordial chemistry of phosphorus on Earth, something that wouldn't be possible to do experimentally, so we simulate it. How do we do it, right? So here is an example of what we call a phosphorus chemical network, which are a wide set of simple chemical reactions involving several different phosphorus-bearing species. So these reactions are all coupled, and we have to study it. So we had what we do here is to predict the rate coefficient, the rate constants, so that we can understand the rate by which these species are decomposed and formed, so that we can run some astrochemical models, so that we can investigate how the abundances of these different species evolve with time within, for example, a molecular cloud, so that we can understand how more complex molecules are formed. So to do this, we have to model and explore the potential energy surface associated with these chemical species. Here's an example of a work I have developed together with Professor Breno. And we have used some quantum chemical packages, namely Orca and MOPRA quantum chemistry software, so that we could model this, at least the most important parts, let's put it like this, some essential features of the potential energy surface. So we are actually trying to connect the reactants, in this case, the collision between atomic carbon with the diatomic PN molecule, to three different possible product channels that we could find here. So we have to connect these, and to do so, we explore this potential energy surface, seeking for what we call these intermediates here, which correspond to energy minima on this potential energy surface. And also we look for transition states, which correspond to saddle points on these potential energy surfaces. So these transition states, they connect two different energy minima, two different intermediates. And once we unravel the structure of these main features of these potential energy surfaces, and we can correctly assign the energies to these species, we can then use what we call transition state theory to predict some reaction rates and then run the astrochemical models. So these modeling of these potential energy surfaces, they are also very useful in the study of the polynitrogen systems that I have already told you before about. So why is it interesting? Because these polynitrogen systems, they actually consist in thermodynamically dissociative systems. When we are dealing with this, we are looking for local minima within the potential energy surface. Why? Because the global minimum is associated with the decomposition of these systems into the most simple N2 molecule. And why is that so? Well, the N2 molecule is it presents one of the most stable bonds, one of the most the strongest bonds within chemistry. So it's a highly thermodynamically stable species because it's connected. These two nitrogen atoms, they are linked through this triple bond here. So it's very stable. And polynitrogens, on the other hand, they are built by single or double bonds between nitrogen atoms mostly. So as a consequence, these polynitrogen systems, they are mostly bound. These nitrogens are bound by single or double bonds, and therefore they present higher potential energy and therefore low kinetic stability. So that's why they correspond to local minima on the potential energy surface, and we look for this local minimum so that we can find some polynitrogen structures that are sufficiently stable to exist for a considerable amount of time. So they tend to decompose, and when they decompose, they dissociate into N2 molecules, and therefore they release large amounts of energy because the N2 molecules are quite stable. And therefore that's why we call it high energy density materials. And one interesting, very interesting, important point here is that the dissociation product is essentially the major component of atmospheric air. So they are candidates for clean energy, like green fuels, because they wouldn't generate like greenhouse effect gases, right? And for practical use, they must also be stored, so they must have sufficient kinetic stability, and therefore we look for local minima that are essentially, let's say, protected by a sufficiently high energy barrier that separates them from decomposition, so that they can live, they can have a lifetime sufficiently large, and they can only decompose if we trigger this decomposition somehow. So in one of my studies on this topic, we have found some stratification of structures into chain-like structures, ring-like, cage-like, and prismatic cage. And as we go from the chain structures all the way to the prismatic cage, we can see a larger amount on average of single bonds between nitrogen atoms. Therefore, we can see a larger amount of energy stored within their chemical bonds. So we can see this stratification of energy content on these structures when we go from chain-like to prismatic cage. We can correlate this with what we call average bond order. On these graphs on the right here, you can see that we have the greatest dissociation energy per atom when we have an average bond order that is lower, and it happens precisely for structures which present mainly cage-like or prismatic cage-like geometries. We have found the main candidate, which is called Prismane, which is this one represented here, because it can release more than 300 kilojoules per mole upon decomposition, and it's also, let's say, protected from decomposition by an energy barrier of around 50 kilojoules per mole. So it's the best candidate that we could find within our studies on this topic. And we believe that this energy barrier gets higher here because when we have prismatic cage or cage-like structures and we want to decompose it into N2 molecules, we will have necessarily to break several bonds simultaneously. So this might not be energetically that much accessible. So therefore, these kind of structures tend to generate larger or higher energy barriers, which is interesting for this specific application here. Well, so coming back to my to the current project I've been working with, let's remember here that our main goal is to produce an adsorbent from biomass, from plant biomass, by chemically modifying its structure to enhance its capability to interact with some specific metal ions, for example, with copper 2 and with zinc 2. And Professor Leandro has a great expertise in doing so. And our goal here is to mainly remove from water bodies cations of copper and zinc. Copper is widely used in electronics and employed as a catalyst, while zinc is very important to the steel industry and is employed in electroplating, for example. But if we are exposed to certain concentration levels of these metal ions, it can cause harm to our health. Some examples from copper toxicity: we can have gastrointestinal damage, liver damage, tachycardia, hemolytic anemia, and there are also some evidence towards Alzheimer's disease. When it comes to zinc, we can have high blood pressure issues, kidney damage, pancreas damage, decreased levels of HDL cholesterol, and also red blood cell destruction. So a remediation for this may come from adsorption techniques. So as I have already said, the goal is to be able to produce some new adsorbents that are actually derived from plant biomass, more specifically in our case from sugarcane bagasse, because this consists on a really abundant material in Brazil that is usually treated as waste. Because this is actually a byproduct of a very important economic activity in our country, which stands for the agro-industry, more specifically the sugar and alcohol industry in Brazil. So for you to have an idea, our 2024-2025 harvest of sugarcane was of almost 700 millions of tons of sugarcane, and each ton of sugarcane can generate up to 280 kilograms of sugarcane bagasse that would be treated as waste. So we try to add value to this renewable and biodegradable material by modifying it chemically to use it as a bioadsorbent to remove pollutants from wastewater, for example. So these sugarcane bagasse can be considered lignocellulosic biomass. If we could zoom in enough on sugarcane bagasse up to the point that we could see the plant cell, we would be able to realize that the cell wall is made up of some fibrous structure that is mainly consisted of hemicellulose and cellulose. Ultimately, these elementary fibrils that made up this material. This elementary fibril is composed of several cellulose strands that several chains of cellulose that entangle with each other. And these cellulose chains, in turn, they are composed of a building block of glucose molecule that are linked together to form a polymer. And the surface of this cellulose polymer is rich on hydroxyl groups, which are a reactive group that can undergo chemical modification. So we make use of the specific properties of this material, which is sugarcane bagasse, to to promote these chemical modifications. Because different chemical modifications can optimize the interactions of the substrate with different types of ions or molecules present in the medium that we want to take out, that we want to remove. So the research group of Professor Leandro has already synthesized several of these materials. One example is the functionalization of these cellulose-based materials, the functionalization with succinic anhydride and pyromellitic anhydride. And we can approach it computationally. So here there are some examples of our model. That is a very complex structure, so we have to simplify. And for example, we represent the cellulose polymer as a smaller oligomer. So we have tried some different sizes of this cellulose chain to represent the cellulose. And here you can see in all the cases the functionalizations. Here is the succinic anhydride, and here is the pyromellitic anhydride. And we could calculate the energy of these structures and compare with the isolated energies of the oligomers and of the isolated anhydrides to see that actually the system is energetically stabilized when functionalized, right? So we can access it computationally to make predictions whether it is stable or not, whether it's favorable energetically speaking or not. And we can also make the bridge between these quantum mechanical calculations and some thermodynamical physical quantities, such as free energy change and enthalpy change and entropy change that accompanies the process of formation of these materials. And this can give us the possibility to infer if the chemical process is spontaneous or not. And if it is spontaneous, is it mainly because of the amount of heat that is released upon the reaction, as the reaction proceeds, or is it mainly due to the raise in the density of states that become available to be spread over by this material and to disperse this energy? And in this case, we would say that the system is the process is entropically driven. So all of this we can predict with computational chemistry. So we can also simulate, for example, infrared spectra. So here we have on the left side the experimental infrared spectrum of this functionalized material. We can see in black here the bands associated with raw sugarcane bagasse before functionalization, and we can see the appearance of this band around 1,700 centimeters to the -1. We can see the appearance of this band on this red line here, which corresponds to the spectrum of the functionalized material. So the appearance of this band is characteristic of the functionalization, and we can corroborate this analysis using theory by simulating this infrared spectrum. We can also see this one up here is the simulation of the oligomer, of the cellulose oligomer without the anhydrides. And when we bond the anhydrides to this oligomer structures, we can see also the appearance of this band here around 1700 centimeters to the -1. And I can also show you an example of this. So we can see the vibration that gives rise to that band, specifically here. So here is the oligomer of cellulose. Here you can see the succinic anhydride, and here you can see the pyromellitic anhydride, and we can see the specific vibrations of the carboxyl groups of the pyromellitic anhydride bonded to the biomaterial. And this is one of the responsible features, one of the responsible vibrations that will give rise to this band that we could see here. So we can also model. I think that I'm already running out of time, so I can just show you some other analysis here. We can do some spin density analysis, and we have done this for this material. Here you can see copper already adsorbed onto the material. We can see that it links to the carboxyl groups of the anhydrates. And we have run some spin density analysis to see that low coordination numbers like this one tend to generate the wrong electronic state of the system. So this is related to copper on the oxidation state 1, but it's not what we want, because the copper that we want to remove from the environment is copper in the oxidation state 2. So we could see through this spin density analysis that we could have the correct electronic state when the copper tended to link to bond to more oxygen from the material. So it favors the correct electronic state when it has a larger, higher coordination number. So we could actually simulate different environments. For example, as we are dealing with a water environment, an aqueous solution, we would expect these metal ions to be coordinated by water molecules. So we have investigated the interaction of the metal ions, the free metal ions, with the biomaterial. We have also investigated the interaction of the biomaterial with the complex water complex of these metal ions. And we have also simulated acidic conditions by protonating the material, and also alkaline environments by deprotonating the material, which I can show you. For example, we can see here, this is one example of a deprotonated case. We can see that we give a gas structure here, and as we optimize the structure, we can see that it tends to gather the functionalizations together because it favors the interaction when we have an alkaline medium. So we have a deprotonation of this group here, so it tends to enhance the interaction and bring these functionalizations together, while if we have a protonated system simulating an acidic environment, we will have these structures trying to move away from each other, which is not favorable. So we won't have significant adsorption within acidic conditions, which match the experimental observations. So I have already ran out of time here, so I just would like to thank you all for the attention, and just to say that computational chemistry is a tool that is capable of enabling the design of molecular systems with specific applications, and it also allows for the rationalization of experimentally observed phenomena. And these applications can range from assisting in the rational development of new materials with environmental applications, such as adsorbents, catalysts, and green fuels, to understanding their underlying mechanism. So thank you for your attention and for the opportunity.
Thank you very much, Matthäus, for a very interesting presentation. Although I must admit, part of it I already saw in Brazil, but still it's good to hear the story again, since I'm not a chemist. We do have a few questions from the audience, so I'll just start from the top, and we'll see how far we get in the time we have left.
Right.
The first question is a question from Mitzi. She asked, how long does it take for a computational calculation for the prediction of a stabilized modified oligomer coming from cellulose? Can you say something about that?
Yes, sure. Should I stop the presentation? May I leave this way?
Yeah, you can stop the presentation unless you want to use your slides to show something. But
okay, if it's needed, I can share again.
Yeah.
So thank you for the question. It's a nice question, actually. It depends. It depends on several factors, because it depends on the level of theory that we are employing, right? So to approach such big systems like this, for example, those videos I have shown, they involve like millions of atoms. So we are within the domain of molecular mechanics. So we have let's say less amount of physical detail. But within electronic structure methods, such as the ones I've been employing to study these systems, it depends. Maybe the most accessible method to use here, it's called density functional theory. So for the smallest models with only a single cellobiose unit or two glucose units, I can run a calculation for a couple of hours, for example. But if we go to the larger one, let's say with 6 glucose units plus the functionalizations to optimize that structure, it can take like days, 1, 2, 3 days. It depends from it also depends on the initial gas structure that we give to the package to calculate. So if we are already close enough to the energy minimum, it will be faster. But if we give a gas structure that is quite unreasonable, then it will last much longer. So a good way to do this is we have to we have to search for previous information on the system. So, for example, we can turn ourselves to some experimental analysis like X-ray diffraction that can provide the experimentally determined structure of crystalline cellulose, for example, and we can get these Cartesian coordinates from X-ray diffraction, for example, and we can start our analysis giving a gas structure that comes from this analysis. So we would most probably be closer to the energy minimum, and then we can make the calculation faster. But depending on the level of theory that we use, if we go to highly correlated methods, wave function based methods, it can take weeks to optimize.
Okay. Yeah, thanks. I can ask a lot of follow-up questions based on this, because I guess this also saves you time. I mean, if you would do everything experimental, then it also costs you a lot of time and money. But I still have a few other questions, so I would like to tackle those as well. I see a question from Nishant. He says, "Great talk. Thanks." He also mentions, "I'm not a computational chemist, but I'm personally interested in CADD, CADD, specifically design small molecules that bind to proteins." He was wondering if you or one of your colleagues is working on these type of projects.
Actually, thank you for your question. Actually, I have never worked specifically with proteins, because these are really huge molecular structures, and to do so, we would need access to really powerful computational resources, and it's not easy here in Brazil. We usually do not have access to such powerful computational resources. It's not impossible. It's actually possible. I know people that work with this kind of topic, but I have never, let's say, adventured myself on the study of proteins. But there's some specific ways of treating it. There's there are specific groups that usually work with this, and they can simulate some what they call different poses of proteins interacting with some specific molecules. This is called docking. It's a method called docking. So if you're interested in this kind of chemical systems, I would advise you to search for this docking scheme, which is quite powerful to a first approach to the protein. Let's say to the protein behavior against an interacting molecule, so that after that you can move to maybe a more robust way of treating it. And I actually have already heard of some artificial intelligence applied to protein folding, which is quite a hot topic nowadays, and it has already presented some really nice results so far.
Okay, thanks very much. I think we have time for one more question. It's a question from Saleh. He says, thanks for the presentation. Short question, how do water chemistry conditions, pH, hydration, etc. Oh, and now something is popping up over the question. Change adsorption performance.
Well, from what we could evaluate from our calculations and our computational results matched very well the experimental observations for these studied systems involving succinic anhydride and pyromellitic anhydride, and involving copper 2 and zinc 2 ions. So we have found that acidic conditions, low pHs, tend to avoid adsorption. So indeed, if we want to remove adsorbed metal ions after the metal ions are adsorbed, we can remove them by washing it with a strongly acidic solution. So if we lower the pH, the tendency is to break the bonds, break the interactions between the adsorbed metal ions and the biomaterial. So if we want to enhance the adsorption of these metal ions on the surface of the biomaterial, we need to make the environment more alkaline. So we must raise pH, and then we will get better results with adsorption. So we can reuse the material after we use it as an adsorbent. We can wash it with an acidic solution so that we can take out this pollutant, these contaminants, and then we can reuse the material again.
Okay, thank you very much. Considering time, we have to leave it at this. Thanks again, Matthäus, for a very interesting presentation. And I also would like to say next week, one of your colleagues is also going to give a lunch and learn, and she will tell a bit more, I think, about the bioabsorbents and the biocatalysts, but then non-focused on the computational chemistry. So if you're interested in that part of the process as well, then I also would like to invite everyone to join next week, same time, same place, I would say, for a presentation of Liliane Catoni. So thanks very much, everyone. And again, the presentation will be sent to you. So if you have any further questions from Matthäus, feel free to contact him. And thanks again, Matthäus.
Yes, I would like to thank you again. I really appreciate the opportunity, and thank you all for attending the presentation. It was really nice to be here. And again, I am open to questions. You can contact me via email. Thank you.
Okay, thank you very much. Bye-bye, everyone.
Bye. See you.